hydrochloric acid. Creating the pH titration curve needs key points in the curve from the titration with the pHs at the initial pH, the pH before the first equivalence point, then the pH at the equivalence point, then the pH before the second equivalence point, and the pH at the second point. First, I found out what the KBs for carbonate ion were, and the KB1 was 2.1 times 10 to the negative fourth, which will be used to calculate the OH concentration. Using this, I calculated that OH and CO3 minus had the same concentration, so I used X for them. And then the HCO3 minus concentration was the total concentration of the sodium carbonate minus the concentration of these. And the pH at this point was 11.36. Then I found the pH before the first equivalence point by using the Henderson-Hasselbalch equation, using the pKa for the carbonic acid. The first pKa was 6.4, the second pKa is 10.3. In this calculation, I used the second pKa because at this point, the carbonic acid is losing one hydrogen. So I used the pKa, then I used the log of the concentration of carbonate ion over this concentration, and I found the pKa of 9.3 at that point. Then the equivalence point for this reaction was when carbonic acid goes to the ions. And this pH is found by using the 2 pKa divided by 2, because this will be the equivalence point where all the pHs come together to find 8.35. Then the pH before the second equivalence point is the same as the first one by using just the different pKa value, because at this point HCO3 minus becomes H2CO3, and here it was CO3 2 minus becomes HCO3 minus. So at this point, use the same concentrations as I did here, just use a different pKa, and found the pH value of 5.4. Okay. And now the last pH value is found through the calculation of the amount of sodium carbonate we have in the solution and the amount of hydrochloric acid. We use 1 mole of sodium carbonate to 2 moles of hydrochloric acid as the overall reaction equation says. So I use the calculation through this stoichiometric problem to find that 15 milliliters of this, we will need 37.5 milliliters of hydrochloric acid. Then the total solution volume will be 15 plus 37. And now I use the table with the initial concentrations and the final by using the moles of the hydrogen ion from the hydrochloric acid and the carbonate ion from the sodium carbonate. And then using all these, the final moles of our product were these. So using these moles over the total volume of our solution, we found the concentration of carbonic acid. And using the Ka1, which I looked up, was 3.98 times 10 to the negative 7. I used the equation to find the hydrogen concentration. I used hydrogen concentration up here, and then the carbonate ion and then the carbonic acid concentration. And these two, since at this point we think that all our sodium carbonate, the carbonate ion, would be used up, then the hydrogen ion concentration, and this concentration would be the same, so they will be X. And then we just plug in the concentration we found up here for carbonic acid and the Ka value, and we find the H concentration by the square root of this concentration times the Ka. And the log of this concentration, we find the last pH value. And then the key points of our reaction, of our titration, were when HCl donated one hydrogen ion to create the first ion we have, or the carbonic acid, which is HCO3 minus. And at this point we only used 1 mole of HCl. And by using a stoichiometric calculation, I found that 18.75 milliliters of hydrogen chloride were needed to titrate the sodium carbonate to create this ion. And this is where our first equivalence point sits, at this pH. And our point before our first equivalent point is at the same concentration. And this is our initial pH that we calculated first. And then here is the volume of HCl used to create the carbonic acid. So here we have 2 moles